Okay, hello everyone and welcome to the SimScale Consulting Partner webinar. My name is Ali Arafat. I'm from SimScale, and before we begin I would like to ask everyone if they can hear us clearly and they can see our screen. So please raise your hand by clicking on the raise hand button. If everything is good, then we would start the webinar. Okay, I see many hands raised, so I guess everything is good to go. Okay, welcome to the webinar. And in this session, we introduce our consulting partner, Streamwise. Streamwise is managed by Dr. Benjamin Rembold, and he would present today the title of the webinar. Benjamin, please.
Yeah, the title today is 3D Online Flow Visualization and Validation Method. We call that ProCap, and as you will see, this is a very efficient way to validate CFD simulation data, but also without CFD it's an efficient way to obtain very high quality wind tunnel data of your flow around an object.
Okay, so before we begin, a few things to announce. This webinar will be recorded, and the recording would be available on our webinar page and also on our YouTube channel. And if you have any questions during the session, please feel free to write it in the questions panel on your right-hand side of the screen, and we would address all questions at the end of the webinar. Okay, so at this point I would like Benjamin to present a little bit of introduction about himself.
Yes, thank you, Ali. So myself, I obtained a master's in mechanical engineering at the University of Karlsruhe in Germany, and then obtained a PhD in fluid mechanics at ETH Zurich. Then worked most of my professional life in R&D environments in industrial firms regarding flow, prediction, simulation, and optimization. And before I then joined Streamwise like 3 years ago, where we focus on highly dedicated consulting in terms of with a focus of fluid mechanics and thermodynamics. And in that sense, I will present today the topic of the flow visualization method ProCap.
Okay, a little bit about myself. I have a background in aerospace engineering, and I've worked at several different research institutes in Germany in the area of fluid mechanics and CFD simulations. At SimScale, I work mainly as an application engineer. My work here is more involved with the product and also the simulations, and I'm also the technical manager for the Consulting Partner Program. So let's start with the then the agenda of the webinar. Before we go into more detail, a brief introduction to what the Consulting Partner Program is. So the SimScale platform provides a simulation platform for which you do not require any hardware or software. So it can be accessed through your web browser, and you can perform high-end simulations using high-performance computing from the cloud. This is very cost-efficient and scalable. We have a large community with thousands of simulation projects and template projects. And we also promote learning and coachings through webinars and workshops. But some point in time, if a user is new to SimScale and he is not experienced in the field of CFD or simulations, or wants to have more insight into the problem he has at hand. At this point, our consulting partners come in and help out the SimScale users or any clients to complete their projects and help them with any critical tasks or any expertise that they require. Our consulting partners have over the years gathered this experience in certain types of problems that the user is interested in, or any general problem which could relate to experimentation or also numerical simulations. They provide their expertise in validations and also in performing or solving complete solutions for the client. And for this matter, we have started this consulting partner program. You can view all of our consulting partners on our website at the consulting partner page. And I will quickly show you where you can find that. So if you go to simscale.com/partners, you can view all of our current consulting partners. And together, the consulting partner program and the SimScale platforms gives you the complete solution to your problem to get the job done. Okay, so the agenda for today's webinar we will start off with some introductions, brief overview of SimScale. Then Benjamin would give you a detailed introduction about streamwise. He would detail you about the ProCap tool, which is used for experimental validation. And then we would take a look at two case studies, the Ahmed body flow and the NACA wing section. And we would see how the results compare from the experiment study to the numerical study. Okay, so we start off with a brief introduction to SimScale. As mentioned earlier, SimScale is a complete platform for simulations. It is accessible through the cloud, so you do not need to install any software, and you also don't require any hardware capabilities. So the complete platform interface can be accessed through your web browser, and you can submit your simulation jobs to high-performance computers that we have. And this gives you almost unlimited compute power. It is very cost efficient. We have very flexible programs, so you don't have to pay a large amount upfront, and you can pay as you go. And also this is for everyone to use, whether people are beginners or experts in simulations. We have a crowdsourced know-how and lots of template projects to already start with. In terms of the capabilities, SimScale provides for fluid dynamics a very vast area of expertise or simulation capabilities. So we mainly cover incompressible, compressible flows, also laminar turbulent. The simulations can be steady state or transient in nature. We cover heat transfer for fluids, multi-phase flows, also particle simulations and conjugate heat transfer. Other than that, we have advanced applications in rotating machinery, propellers, turbines, compressors, also porous media and free body motions. Okay, now I would hand over the presentation to Benjamin to introduce us to streamwise.
Thank you, Ali. Yes, since we focus on ProCap, I will keep it short on the streamwise side, but still a few words to our company. We are a spin-off of ETH Zurich. We exist now for 6 years, and we have essentially 3 columns that we rely on for projects for our customers. The first column is troubleshooting, and this is when customers come to us when they have a project which is ongoing and they are stuck with some fluid or thermodynamic problem on their way. So what we do for them then is data analysis. We really sit together with them in workshops and try to understand their problem, and then go deeper with system modeling and redesign, and then we also continue and design simulation campaigns or validation experiments, and then of course try to come up with a solution and design modifications to actually change their geometry or their setup such that it works at the end. Second column is design optimization in general. So if our customers are in a design phase of a new product, then they might have fluid or thermodynamical issues, and we do for them analytical and empirical and also numerical modeling to actually solve their issues and come up with optimized design solutions. So it starts with an identification of the governing principles, and then of course it involves parameter studies and optimization at the end before we then come up with an optimized solution. What we also do, product development support. That means we really go with our customers together through the entire development cycle, and at this point we can open up all the fluid mechanical options that there are to come up with very innovative solutions. We go through concepts and feasibility studies, and then narrow down options to come at the end with the optimal solution for the particular problem. And of course we also do then prototyping and proof of concept together with our customers to ensure that the concept at the end actually works. Now, a typical project project timeline looks like this, starting with a fluid problem. We go there and make a first analysis. That means we go there, we sit together with the customers, we do workshops, we dig in their old data, we dig in all available information and trying to understand what's the matter, what's the issue, and then in the second step we propose a way how to attack the rest of the problem. That is, that could be a very complex simulation campaign. It could also be a simpler way to attack it with, let's say, 1D modeling, also semi-empirical, analytical, or empirical methods are available. The general guideline is to start from simple and then become more and more complex. We involve all methods of data mining, we employ measurements, we do CFD, and we put all the data together at the end to come up then in the next phase with design proposals and of course a verification at the end that it works. And of course we also lead our customers through various cycles. I mean, this is just the normal thing in development that we have to go back sometimes. So streamwise covers really the entire timeline from the problem side until the end to the verification. Now, looking at tools that we have to do that, we have strong background in computational analysis, but here also I have to say that we start with simpler methods and then becoming more and more complex if necessary, but only if necessary. So we start with a problem-specific 1D model development that can also be analytical, that can also be just experience, so it can be very simple on that level. But then we have experience with the various 3D CFD simulation tools. This is commercial solvers, this is OpenFOAM, and that is also the SimScale solvers, of course, but also proprietary codes. And of course we are familiar with all kinds of problem-adapted post-processing and various simulation types, as Ali has already mentioned. Very important for us is also the experimental analysis side. Three employees at streamwise have a very strong background in that area. And also here we have the level of complexity. We start with this simple, and then it can get more complex if the problem has the need for that. So we have experience with high-speed imaging. Then we have also infrared temperature measurement experience. And then when it comes to optical sensing, our employees have a strong background in that area. Particle image velocimetry, PIV, and laser Doppler anemometry. These are the gold standards, let's say, in fluid mechanical measurement principles. This is something they have done on a regular basis. And then we also come to more, let's say, less well-known methods like background-oriented Schlieren, pressure-sensitive paint. These are some more exotic methods, but they can be for particular problems very interesting. We have also access to the wind tunnel of the ETH Zurich, where we can apply various measurements, and we will see some results today in this webinar. And we have also some experience in wireless sensing, where we have developed a measurement platform to acquire local measurement data with a wireless sensing platform. But we will not focus on this today. So let's focus on ProCap now. This is the main topic of today. So let's explain how that really works. So as I say, it's a measurement method for the wind tunnel data. So it's really to acquire 3D data of flow around objects. Now, probably most of you know the classical smoke probe, which is always seen on pictures of wind tunnels. And the advantage of such a classical smoke probe is that the user who actually applies it in the wind tunnel, he can focus on areas where the flow is interesting very quickly. So it's very intuitive for the user. The engineer in the wind tunnel, he goes to he focuses in let's say separation zones and finds out immediately how the flow topology around the object he looks at looks like, and so he can build up very fast a knowledge about the flow within his mind, and he can focus on interesting areas. And this is why. And the reason for this is because there's a man in the loop who actually understands what's going on. The main disadvantage, however, is that you have no documentation of this available. It's only in the brain of the user, and the data is not really available later for comparison, and it's not quantitative. You have just an idea that the flow more or less looks like this, but you cannot really say that one object is better than the other. So no quantitative data is available. And this is really the main idea behind ProCap, that you combine the advantages of a classical smoke probe with 3D optical tracking methods. So we keep all the advantages that an operator in the wind tunnel has a manually operated probe and can focus on interesting areas of his object he's looking at. And then at the same time, it's a real 3D flow measurement. And how this is done is that the probe is at the same time tracked with a 3D camera system. So once the operator is moving his probe in the wind tunnel, the 3D camera system tracks the probe and online displays the data acquired on the screen in the wind tunnel. So this gives an online feedback to the operator, and we will see later in movies how this really works. And he can build up knowledge about the flow exactly as he could do with a smoke probe, but he can in fact acquire really 3D data on the way. So the setup times of the measurement method is very short. Once you have your camera system installed and the probe is calibrated, you can just put in the object in the wind tunnel and go, and then focus on the areas that you're interested in. You can also measure very large-scale models, because you do not automatically acquire data in, let's say, boring areas where the flow, where nothing is going on in the flow, but you can focus automatically on separation zones, on recirculation zones, on some vortex shedding areas, whatever you might be interested in the particular model. Available quantities are in general velocity and pressure. This is with the 5-hole probes, which is a classical probe I show in a later slide. But technically you can, in principle, combine the method with all available probes. So temperature, for example, could be done, and also humidity. It's not really the options are very wide. And I must say that the entire system was developed in cooperation with the ETH Zurich, and all the measurements I present today were also obtained in the ETH wind tunnel. Now let's position ProCap in the field of other methods that are available to acquire data in wind tunnels. Let's look at the x-axis here, which is cost, complexity, and time, and then you have accuracy on the y-axis. So if you look at the classical smoke probe, it's very inexpensive. But it's at the same time not accurate. You get only qualitative data, so it's in the lower left corner. But on the other side, if you look at particle image velocimetry or traverse data in wind tunnels, that's very complex. It takes time to set up. It also takes time to acquire data, especially for traverse data, but the accuracy is high. And what ProCap is a lot faster than PIV and traverse data. It's not as accurate, but it's very close to the accuracy of these two methods, and really the advantage is that it's fast and you can focus in areas that you are interested in. Now, one example is it's here in a wind tunnel where you have an experimental aircraft in there. You have you see the aircraft in the front of the picture, and you see the engineer who actually handles the probe. And you see in the back the online display of the results. You see online display of the CAT data of the experimental airplane, and you see also in the projection you see the probe, which is also displayed in the picture. So you can really focus on the local data that you acquire. So the data which is projected on this plane, the red and green and blue colors, this is really acquired data in the wind tunnel, and the operator can focus on the areas where something's going on, and he can refine the data by just spending more time measuring in this area. And of course, the data is not only available for during the measurement as a feedback to the engineer, but it's of course later available as a 3D data set for comparison in the post-processing. Now, another example is a sailboat. The setup is the same. You have a CAD model projected at the same time, and I guess you would agree that the flow around such a model is indeed a complex one. And also, if you would like to set up a traverse or so to acquire data around such a model, it will be very difficult that you don't have crashes of a traverse with the model. So with the probe here, it's very intuitive. You can just go to the locations where you're interested in and focus on this area and acquire the data, and you are done. It's very, very intuitive. This is the probe we have used for the two measurements you've seen on the last two examples. It's a 5-hole probe. You see here the 5 holes at the tip of the probe, and then you see also the markers. Here we have 4 markers on the probe, which we use to optically track the position of the probe in the wind tunnel in real time. That's one way to obtain velocity and pressure data. But we have also used another probe here. This is a hot wire probe for lower velocities, and this was used for flow for the internal flow in a passenger car, for example. You see the shape of the probe is a little bit different. You have other optical markers, but the method is again the same. Now, I have now briefly introduced you to the method, but I guess it will become more clear when we actually look at examples. And for this, I hand over to Ali again. He will explain the case and some simulation data for the case, and then I will show you some measurement results afterwards. Ali.
Thank you, Benjamin. So the first case we take a look at is the Ahmed body flow. It's pretty standard in external aerodynamics, and we would see both the comparisons for the data acquired by ProCap through experiments and the numerical simulations done on SimScale. Okay, so a brief overview of the case. So the Ahmed body model is in standard dimensions in meters. The inflow velocity is at 17 meters per second. We have incompressible turbulent flow. The main purpose here is to study the wake profile in the wake of the Ahmed body and compare the data with the experiment. In terms of the setup numerically, we have a large domain around the body, so we only take half of the body and use a symmetry condition. We have an inlet at the front and a pressure outlet at the back. The side walls are then taken as a slip condition. Just to make a note here, the wind tunnel data that will be shown is acquired from ETH Zurich by streamwise. Okay, we would first take a look at the numerical setup, and before we go to the live presentation of SimScale, some images of the domain meshed. So you can see on the left picture the complete domain which is meshed has different gradings or different mesh sizes, and it becomes finer and finer as we go close to the body. On the image at the right you can see highlighted in red the Ahmed body and a very fine region around it to capture the flow in good detail. If you zoom in on close to the body, we also have a layered mesh. This layered mesh would capture really the boundary layer and would give us the optimum results with respect to what's going on close to the boundary. Okay, at this point I would shift to the live demo of the Ahmed body project in SimScale. Okay, so what you see now here is the interface of the SimScale platform in the workbench. And the first tab here is the Mesh Creator tab. You can import your CAD geometries and upload it to the platform. And the first task here is to mesh the geometry for simulations. What we are looking here in the viewer is the Ahmed body case. You can see the mesh is really fine, so I would zoom in and show you the Ahmed body. Okay, so now you can see the mesh in detail and you can examine it. This is a fully hex dominant mesh. It's also very flexible to create such meshes and you have a control on a lot of parameters. For this particular case we used some different refinements starting from refinement of the surface, region refinements which refine the complete volume, to a layer mesh refinement to capture well the boundary layer. So you can watch it in 3D, also examine the cut sections of the mesh in more detail. I would now quickly jump on to the simulation setup just to show you how the look and feel of the platform is. So the main analysis type chosen for this simulation was incompressible turbulent model and steady state analysis. It's really intuitive to follow the simulation setup. You can just follow the simulation tree and complete each entry which is required to complete the simulation setup. The main key points here are to assign a mesh or a domain for the simulation, which is again the Ahmed body case. The next is to assign the material of the flow, which is air in this case. Then the main task is to assign the boundary conditions, for instance the inlet, the outlet, and the symmetry planes. In terms of once you're done with your setup, you can just create a run, and these runs are performed on high performance computing clusters that we have, and no hardware resources are used from your system. In terms of time it takes to do this particular run, it took around 170 minutes, so just over about a few hours to complete this simulation, and that was it. Okay, now I would go back to the presentation and show you how the data can be acquired with the ProCap tool, and then we would look together at the results in the post-processor. Also, we have on SimScale the online post-processor. where you can see your results in detail. I have already saved some screenshots of the Ahmed body. What you see here now is the velocity contours with the velocity streamlines. And in the second picture, you see the pressure distribution at the front of the Ahmed body with high pressure regions. And for more advanced post-processing, you can even download your results and post-process them locally. Okay, I would now go back to the presentation and hand it over to Benjamin to show you how the measurement data is acquired from ProCap.
Thank you, Ali. Yes, maybe two comments before we start with this. First, the wind tunnel data was recorded at ETH, and of course, and the second comment is it's not, a real live demo in the sense that I'm actually sitting in a wind tunnel. No, I'm not sitting in a wind tunnel. I'm sitting in front of a computer, but I will show you in terms of pictures and movies how it actually works for this particular problem, and we also show you the real obtained data. Now, so you would understand later how the procedure works in detail. You understand also how the quality of the obtained data is, and you understand the process of comparing CFD and the measured data at the end. So once again, how the method works and how the procedure of measurement works. So first of all, you have to set up the system in your wind tunnel, and I say that because most of the time measurement systems are really installed in a wind tunnel and they belong to the wind tunnel, and you cannot measure somewhere else but in the one dedicated wind tunnel. But ProCap is very modular, and it can be easily installed also in other wind tunnels in a short amount of time. I say now, let's say 2 hours, and you have the entire system set up. So you can get all the system in a passenger car, go to any wind tunnel, build it up, and start to measure. So at the beginning you have to set up and calibrate your camera systems, and then calibrate the probe if not yet done, and then you are ready to go. And if you then want to do the actual measurement, then you have to position your body. In that case, it's the Ahmed body in the wind tunnel. You have to set the measurement volume that you would like to acquire data at. In that case, it's the separation zone where the vortex roll-up in the back of the Ahmed body occurs. And then you have to set the wind tunnel speed, and then you're ready to go to acquire data and to visualize them on the go. And how this looks, how that can be tracked online. One possibility to do that is by, I call it voxel eating. So you have the Ahmed body, and you see on the screen in the wind tunnel at the time you're measuring there the volume that you would like to obtain data in by so-called voxels, and you just go ahead and move around with your probe and eat away these voxels. That tells you as an operator you have once you have the voxels disappear, they tell you you have enough data acquired in these areas. But there's a more intuitive way to obtain feedback, and this is by direct visualization. So you define planes where you would like to acquire data, and online you see how your probe moves, and you fill up the white plane with data acquired in the wind tunnel. And then you can see the structures in the flow immediately, and you can spend more time in areas where you have more structures, let's say shear layers, vortex, roll-ups, and so on, and get a refinement of the data in these areas. So at the end you have data like this, and of course here you have it visualized only on a plane, but in reality you have a 3D data set at all the locations you have been with the probe during the measurement. Now in reality it looks like this, and I have prepared, or my colleague has prepared a small movie And I have to explain this in a little bit more detail. On the lower right corner you see the actual Ahmed body. It's very dark, but you see the back of the Ahmed body and you see the real probe moving in the back of the Ahmed body. Then on the right hand side of the movie you see the screen that the operator sees in the wind tunnel. So this is the live feedback he can see during measurement. And on the big 4 screens you see are just alternative screens you can also see. So you have the option of the voxel eating on the upper left corner. So the probe goes through the measurement volume and eats away the voxels, and such telling the operator where the data density is already high enough. On the right upper screen you see various planes where the operator has already obtained data, and you see that the vortex roll-up is very stable and it changes only slightly. I restart again. Focus again on the upper right corner where you have the probe moving around in this plane, and you see how data is online changing when the probe is actually acquiring more and more data in this particular plane. So the data is then refined and becomes stable at the end. In the lower left corner you see another way to visualize data. This is ISO contour of velocity, I believe, and on the lower right picture you see streamlines which are online computed through the velocity field which was obtained with ProCap. So I hope this video gives you some impression how the data can be acquired, and to obtain the data set in this quality in this volume it takes maybe at maximum half an hour if you want to really do it in detail. Now let's continue. Ali, can you move on to one slide?
Okay.
Thank you.
Now
I hand over to Ali.
Okay, thanks. Now let's take a look at the acquired 3D results from the ProCap tool that you just viewed, and the comparison to the numerical simulations performed on SimScale. In this picture you see on the left the ProCap experimental results from streamwise, and on the right side you see the CFD simulation results. I would show you how this comparison can be done interactively, and also you can compare the data in more detail. So I would turn now to the post-processing tool ParaView. So the interface you see now is of ParaView software. In this we have in the left panel the results from the experiment done by streamwise, and on the right side the CFD results. Both these sources are added to this window, and I can manipulate the data in many ways. Just to tell you how interactive this is, I can move around the body, I can take different slices where I'm interested in, and I can also use the available data to calculate more data. What this means is from the raw results of velocity I can compute vorticity, I can look at the velocity vectors and whatever I'm more interested in. So I will show you how this can be done by simply adding some calculators in the ParaView tool. We can calculate the stream lines or the velocity vectors. So what you now see is the velocity vectors of the trailing vortex from the Ahmed body from the ProCap tool. And if I would just go and turn on this for the numerical results, so you can see a comparison, really good comparison of the experiment data collected by the ProCap tool and the numerical simulations. And this is not only visual data, but you can also extract really numbers and qualitative data and quantitative data and also compare them. So this tool, ProCap, is very useful that you have your experiment saved, all the data that you have for future references. You can extract plots from it, and use it for different studies. So your data is not lost like a conventional smoke probe, but available for you later on. For the CFD simulations, we already know the data is generated in vast amount of quantities, but we don't know whether it's close to the experiment. So this tool brings you a good comparison of your CFD results with experiments to validate your simulations. Okay, I would now move back to the presentation and move with the second case, which is the NACA 0012 wing section. Again, the data from the wind tunnel was recorded at ETH Zurich. A quick overview of the setup. The main purpose here is to capture the wing tip vortex for the wing section. This is of course 3D flow. The inflow velocities are around 12.4 meters per second. The angle of attack here is taken as negative 11.5 degrees. The airfoil span is 1 meter and the chord is 0.2 meters in dimensions. The point of interest for us is really at the trailing edge at a distance of about 0.2 meters behind to see the wingtip vortex shedding and the effects. A quick overview of the domain and the boundaries. So for numerical simulations, there are some criteria that you need to fulfill. One of them is that your domain boundaries have to be quite far away. Some standards say that it should be more than 100 chord distance. In this case, we have taken around 50 chord distance in the X and the Y dimensions, which are the horizontal and the vertical dimensions, and about 2.5 times the span of the wing in the span-wise direction. Here the boundary conditions that we used for the numerical simulation were pretty standard. Symmetry was used for the far side and slip condition was used on the wingtip side. For the inflow and outflow, a custom boundary condition was used which mimics the free stream conditions. Again, to show you the mesh for the NACA wing section, you can see the complete domain and how the mesh becomes finer and finer as we move close to the object of interest. In the close-up picture, you can see a very fine mesh on the wing with even finer mesh at the leading edge, the tip edge, and the trailing edge. Okay, a zoom in of the layer mesh. You can see in this case we have taken only 2 layers. This is because we want to keep the mesh sizes low for such a sample project, but for real analysis, or if you want a very good validation, it is recommended to have at least 5. Close to 7 would be appropriate. Okay, I would now switch to the live demo of SimScale to show you the setup of the NACA wing section. Okay, so you can see in the project, the same project, we have the NACA airfoil geometry. This is a very high resolution geometry. This makes sure that we avoid any non-physical effects or early flow separation phenomena. I will quickly load the mesh. So what you see now here is the complete outer domain. So if I hide these outer domain boundaries, you can see inside the wing section itself. This is again a very high quality hex dominant mesh. We have a lot of control on the meshing parameters, and you can define a lot many refinement zones as required. In this particular mesh, I have used from region refinements to surface refinements and also edge refinements to capture really the profile well. Just to give you a quick overview in terms of the size, this is around 3.3 million cells, 3D volume cells in size, so not too large a mesh. In terms of the simulation setup, for the flow velocities we still consider it as incompressible flow with turbulence modeling using the K omega SST model, which works really well. Again, this is a steady state simulation. What is of interest here is I will show you how to set up the free stream condition. As mentioned, it was a custom boundary condition where we specify velocity as inlet outlet. What this means is the inlet value is specified by us and the outlet value is free, and it is calculated from the interior domain. Similarly for pressure, the standard pressure is used for the boundary. Other than for the outlet, the pressure is calculated from the interior of the flow. The same goes for the turbulent kinetic energy and the turbulent dissipation rate. The values for the inlet are taken as specified, and for the outlet these are calculated also inside the domain. In terms of the simulation time it took to perform this analysis was just above an hour, so 78 minutes. So pretty fast for supercomputer, and you can even run very big mesh sizes very quickly. I will quickly go on to the saved screenshots of the results. For the wing section, what you see here in the image is the velocity magnitude and the tip vortex captured by the streamlines in the image. The second image here shows the pressure distribution. Just keep in mind this was a negative angle of attack, so you have higher pressure on the upper surface, and the streamlines in white are showing you the wing tip vortex. Okay, I will now switch back to the presentation and hand it over to Benjamin to show you how this was done with the wind tunnel using the ProCap.
Thank you, Ali. Yes, again, I mean, the procedure of measurement for this particular case is identical to the one we've presented with the Ahmed body. For the presentation of results, in this case we have focused on projection of online data on a predefined data plane, and you see static pressure contours and velocity vectors. And I will start the movie such that you can understand how it actually works. So this is projected online on the wind tunnel wall or on a screen outside of the wind tunnel that you can see through a window, where the operator moves the probe behind the wing, and then you see that the data is very stable, so the flow develops, and the vectors you see, they only move a little bit when the data is refined. That gives very intuitive feedback to the operator. Now he's actually looking for the trailing edge vortex, for the tip vortex I mean, and there you can see static pressure minimum. And finally, you can also fill up the rest of the contour plane, and you see that there's not, in terms of pressure, not too much going on, but the velocity contours are going around the tip vortex. I will stop at this position and continue to other visualization methods. So in that image you see the trailing edge dynamic pressure loss, where you see this blue line where you have really the trailing edge pressure loss. You see again the velocities vectors around the tip vortex. Another way is to look at post-processed data, and this is the curl, the vorticity computed from the data, and that can be done very conveniently, of course, and you can visualize the data the same way, and you can also identify the tip vortex by looking at isosurfaces of vorticity in that case, for example. Then we continue to look at a comparison of the results obtained by ProCap and Streamwise, and for this I hand over again to Ali.
Thank you, Benjamin. Okay, here you see the results side by side for the experimental data from ProCap on the left-hand side and the CFD simulation results on the right-hand side. I would again go to the live presentation on the ParaView software. So what you see now is again the interface of the ParaView software with both the results loaded. On the left we have the data from ProCap. On the right hand side the CFD simulation results done on SimScale. What you see here is now the velocity magnitude contours. You can see a good comparison of the vortex which is captured from the wingtip. Slight changes in the flow you see close to the trailing edge which is away from the tip. This can be due to the different nature of the flow based on the experiments. Because the simulation is entirely done in turbulent flow regime, in real life we can have a transition or a semi-turbulent flow, and this can cause a little bit of differences compared to numerical simulations. So already you can see based on different parameters how the results would look like and where you can justify your differences based on the experimental results and the CFD results. Again, to show you how you can manipulate the data to see more, we can turn on the velocity vectors for the ProCap case and also for the CFD case. I would show you a zoomed in view of it, and you can see a good comparison. Slight differences seen here for the wake. Other than that, we have the same magnitudes for the velocity of the vortex as the experiment. Again, this data can be outputted in terms of plots or manipulated to show you different data sets, and it's pretty flexible in terms of data manipulation. Okay, then I would turn back to the presentation. Okay, time for some wrap-up. I would now hand over to Benjamin to conclude some of the points.
Yes, let's wrap up ProCap. I hope you could get a feeling how the data acquired by ProCap are in quality that you can really deliver fully 3D data from experimental data, and this is the question that I very often get. People ask me, is this really measurement? Are you sure? Is it not the CFD data? And I have to explain again, no, it's actually 3D data obtained in a wind tunnel. And the obtained data can be readily analyzed and compared with CFD using standard post-processing tools, and it can also be done standalone, offline. And what we at Streamwise offer for customers is measurement services with ProCap, and of course based on the data we offer also aerodynamic optimization campaigns. We also have knowledge in the simulation, on the simulation side, where we can support you. And in general we deliver in-depth consultancy in fluid and thermodynamics. And of course you find more data and more information about Streamwise on our webpage, and you will also find some more details on ProCap on our website. And afterwards the tutorial from this webinar will also be uploaded on the SimScale platform, and you will find also the forum, workshops, and also the recording of this webinar, and also documentation of the SimScale platform. With that, I invite you to contact me at any time if you have questions, and we will later on also at the end also answer the questions we have received now during the webinar. But before that, I will briefly hand over to Ali again.
Thank you, Benjamin. Some quick links that we have at the end of the presentation. The project that was shown with the numerical simulations is public on the SimScale public project library. You can just go to the project library and search for streamwise webinar project. This is freely available to everyone who has a SimScale account, and you can view the project, also make a copy for yourself, and carry on with the simulations. I would quickly go now to the library to show you the project. So this is what you see here is the project page with a snapshot of the results that were shown. The complete setups are inside the projects. You can see how it's done. Also in our public project library you will find a number of other different projects. Our consulting partner streamwise is available to solve your problems, help you out with numerical or experimental validation of your projects or any problems regarding external aerodynamics. Their website, you can reach out at any time. If you require more details regarding the ProCap measurement tool, you can reach out at the contact email ID. We also have a streamwise at our consulting partner page. You can also access or get in contact with them by just visiting the page and clicking on the button to request a code or get into discussion. With that, I would ask you if you have any questions, just put it into the questions panel, and we would now start to answer your questions. Thank you for joining, and please put your questions in the panel, and we would start in 1 minute. Okay, we already have 3 questions in the panel, so I would start with the first one. It seems to be more related to the numerical simulation of the Ahmed's body. This is placed by Marco, and he asks, why are only 2 to 3 boundary layers on the Ahmed's body? I have read some manuals for that. A turbulent flow, at least 8 to 20 layers are necessary. Yes, in fact, it's recommended that to capture better the boundary layer, you should have at least about 7 or 8 layers. For this demo project, we did not have so many, just to keep the project size low so that users can easily copy it. For a proper validation, which we already have in our documentation, if you just go to simscale.com and to the documentation page, I can show you over here also in the learning section, then to documentation, and in the left section you can see all the validation cases. We already have a validation for the Ahmed body flow, and this validation case uses more layers to get more accurately the results. The second question is placed by Ahmed, and I guess Benjamin, looks like it's related to probe, so go ahead.
Yeah. Yes, the question is by Ahmed, and it has two parts. The first part is it was mentioning that the upstream boundary condition was placed too close to the Ahmed body. You are probably right with this, but again, I mean, this was a demonstration purposes, and we were not aiming at a really detailed comparison. It's with the background in mind that the problem size should be small enough such that users can actually handle that. But I agree, it's probably too close to the Ahmed body. And the second part of the question is that it's also a comment actually that 5-hole probes cannot really be used in backflow regions of the flow. And Ahmed is absolutely right with that comment. I mean the 5-hole probes have an angle of acceptance which is directed towards the probe. So if you have backflow, you will not correctly measure the flow. But that again is a problem that is inherent to the 5-hole probe. But you can still use the data to visualize in the shear layers. And if you have looked closely at the comparison of that Ali showed, measurement and experiment, you see also that exactly in the separation zone the data will not compare well, and this is due to the 5-hole probes that do not measure correctly in this area. This, however, is not it's not an issue by ProCap, it's an issue by available probes for such type of flows. You can't combine any other probe which is more suitable if you wish to ProCap, but again, it's also a validation method which has let's say an engineering quality, so you have to focus on the areas where data is really makes really sense, and in the backflow region you have to know that you will not have the correct flow data acquired by the 5-hole probe. I hope that answers your question. And then I will continue to the next question by Gautam Das, and I guess this also relates to ProCap. The question is ProCap experiment virtual? And the answer is no. It's a real experiment in the wind tunnel. I mean, you have an actual model, you have a real wind tunnel, you have real wind, and you have a real engineer sitting there with the probe. However, he has online data available for feedback during the measurement, such that the engineer can focus on the real interesting areas of flow around his object, and as such he can first of all focus on these areas, acquire data in a fast way because he focuses, and third, he can actually acquire the data as a 3D data set for later comparison. I hope this answers your question. Now I continue to another question, to the next question. I read it. It's in calculating local flow velocity, I assume that the probe alignment is detected and tunnel flow is perfectly lined up with tunnel axis, right? Well, the probe alignment is of course detected, so the position of the probe and the direction of the probe is determined at any time, in any instant in time, and the movement of the probe itself is also taken out of the measurements, because it can be that the probe itself by the velocity of the probe changes the velocity data, so this is calibrated out of the data at the end. But the flow is in the wind tunnel is perfectly lined up with the wind tunnel axis only at the inlet, not in the separation zone in the vortex region, of course, and this can be captured by the 5-hole probe, after all, not in the fully separated backflow region as I mentioned before, but of course in the other regions. Again, I hope this answers your question. Please contact me later if it's not exactly what you meant. Then I continue to the next question by Alex. The question is, well, it's not really a question, it's just a comment that he likes the results. Then I thank you, Alex, and continue. And also Marco gave a comment that it's answering his questions. Okay.
Okay,
then I continue to
Benjamin.
Yeah, this is maybe a question for you.
Yeah. Okay.
Yes,
I'll
Ali?
take the next question from Krishna. But before
Yes.
that, just a comment to Alex. The ProCap is not a simulation tool, so just to be clear, it's a data acquisition or from the real wind tunnel analysis from the physical experiments, and the SimScale platform is the simulation tool. So because you mentioned
Aha.
that both these simulation tools show a good comparison. So just to be clear, the ProCap is real experimental data visualized alongside with the simulation results from streamwise from SimScale.
Yes, thank you for clarifying, Ali.
Okay, the next question from Krishna is why isn't a standard C-grid topology used for the airflow meshing? Does this not work well with the open form? The answer to this question is that the meshing approach that we're using on SimScale really has a, a rectangular bounding box, you can say, or bounding domain. And if you work with the C-grid topology, many structured meshes use that approach, and the measure that we have is more a hybrid measure. So you don't have to join point by point like you do for a C-grid. You can just have a box, and the mesh automatically, based on your refinements, generates a hybrid mesh which is locally structured but globally unstructured. This is easy to use with complex geometries and also performs well in most situations because you can because this is a hybrid approach, it takes less time to make a mesh for a very particular geometry, for instance. So it's like a global approach for whatever geometry that you have.
One comment from my side to Krishna. Also, of course, classical C-grid topology for airfoils is a very good approach, and it also does work together with OpenFOAM. It's just the meshing approach is slightly different here. But if you have C-grid topology grids that you would like to upload, you can go ahead and do so, no problem.
Yeah, of course. You can upload all of your meshes that you have from other tools, convert it to the OpenFOAM format and use them for simulations also. I hope that answers the question. Then I would move on to the next question, which is from Gautam. He says, how flow separation is visualized? I guess, Benjamin, you can first explain the experimental part.
Yeah,
Then,
I mean, this is if you look at flow separation, let's look at the Ahmed body, and then you have the recirculation zone after the Ahmed body. What you visualize is actually the shear layers, because you can resolve them with the ProCap method. And also you see the loss in dynamic pressure, and that's the way how the separation is visualized. And we have already clarified in previous questions that the backflow will not be correctly captured by a 5-hole probe, but still it gives you a good impression where the separation zone is. It will not give you the exact flow topology in the separation zone, but it will tell you where it is, and it will help you to optimize your model. And in the simulation, maybe you can maybe you, Ali, can briefly comment on that.
yes, for simulations or CFD analysis, there are multiple ways to actually visualize flow separations. Start from 2D streamlines or surface line integrated contours to analyzing the velocity vectors themselves. Also, if it's close to the boundaries and you're interested in calculating the separation point, you can calculate the wall shear stresses, and you can see when they're getting negative, that's the point of the separation and the reverse flow. So there are multiple methods that you can use depending on how detailed you want to go. Okay, I hope that answers the question. Then we are lining up.
Yeah, I guess the next one I will take. It's by Alex, and the question is whether ProCap, in terms of cost, is also lower than other tools like PIV, in terms of complexity in the graphic. And the answer is Usually in wind tunnel, I mean the cost is somewhat scales with a wind tunnel time. I mean if you go to a commercial wind tunnel, it's very expensive and you pay by the hour. And in that sense, it's definitely less expensive since you can acquire data in the interesting region a lot faster than you would, for example, with PIV. And in that sense, it's definitely less expensive. In reality, I guess it would work that you book like half a day of measurement time, and you can just get more cases done in that time. You can modify your flow situation and optimize with that half day, and with PIV you could maybe only run 1 or 2 cases. So this would be the reality, but in terms of cost per acquired data, it's certainly lower. Then we continue. I guess we have some more comments, and the last comment, there's one question about security on SimScale. This is for you, Ali.
Yeah. Okay. On SimScale, this is a cloud-based platform, and all data is encrypted by really high standard encryption. This is end-to-end encryption. All your data is hosted on our high-performance computer servers. And these are also backed up by encryption. So all data transfers is backed up by encryption. Once you download the data to your own computer, that is the point where the encryption part ends. So once you host the data on your system by downloading it, then it's not encrypted anymore. But every other action that you perform is all encrypted on our servers. This would also come to the next question, which says that where do we host our servers? Right now our servers are located in Europe. I cannot tell you the exact country or location of it, but we also scale according to requirements of our customers. So if you are in US or in Australia, then we can acquire servers which are close to you to give you the optimum experience. And these are normally on-demand servers also. If you see that you need more compute power, more than 32 cores per job, then we can also supply on-demand computing power.
Okay, then there's one last question I think I will take. It's about whether streamwise would provide services also for other countries, and the answer is definitely yes. We would do that. As I mentioned, for ProCap, the method is modular and can travel. And actually, one of the pictures, one of the data was obtained in the wind tunnel in New Zealand. So we have moved the system already once around the globe, and we can do it again. And Alex also asks to show the first slide again. Could you do that, Ali?
Yes, definitely I would. Okay, is it the first slide or about the... I think it's your introduction.
It's, I guess, number 3. Yeah. Yeah. Does that answer your question, Alex?
Okay, Alex, if you have a particular question for Benjamin, please let us know.
Yeah. If not, I guess... Ah, okay.
Okay. If you're interested to know Benjamin, you can freely contact him.
The contact data you'll find on the various links.
Okay, another question from Alex.
No, I don't see a problem, Alex. This could be done. I mean.
Okay, great.
Super.
Okay, that's good. If the audience does not have any more questions, then I would thank everyone for joining this webinar, and then we would conclude the session.
Goodbye to everybody from my side.
Okay, thank you everyone, and have a great day, and bye from SimScale.
Bye-bye.